Hello and welcome to this tutorial using the double integration method to find deflection in beams. In this tutorial, we'll be looking at a cantilever with a UDL, but the trick in this one will be that the UDL is only partially loading the span of the cantilever. Let's have a look together. In this example, we have a cantilever beam which is fixed at A and free at C. The total length of the beam is L, and a uniformly distributed load of an intensity W is applied over only part of the span from A to B, which is of a length of A. The remaining portion from B to the free end C is unloaded. Because the loading does not extend over the full span, the bending moment expression will change at point B. This means we need to divide the beam into regions when we're forming the governing equations. In this example, we're asked to determine the equation of the slope, the equation of the elastic curve, and the slope and deflection at the free end, which is point C. The key feature of this problem is the partial loading, which will require a piecewise analysis using the double integration method. We have already covered this method in great detail, so here is just a quick reminder. We assume that EI is constant. We then sketch the expected elastic curve and recall the boundary conditions. In this case, zero slope and zero deflection at the fixed end. We next determine the bending moment expression, mx. If loading is discontinuous, we need a separate expression for each region. We then integrate once to obtain the slope equation and integrate again to obtain the deflection equation. We shouldn't forget to add the constants of integration at each step. And finally, we'll use the boundary conditions and the continuity of slope and deflection at the interface point, if there is one, to determine the constants. Once constants are known, we can substitute the required value of x to obtain the slope and deflection at any point of interest along the structure. Let's begin by sketching the expected elastic curve. This is a cantilever fixed at A and free at C. At the fixed end A, the deflection and the slope are zero. The load acts only from A to B, so in this region the beam curves downwards because the bending moment is present. The curvature is greatest nearer to the fixed support where the bending moment is largest. At point B, the loading stops, and from point B to C there is no distributed load. As we move towards the free end, the bending moment reduces to zero, and therefore the curvature reduces to zero. The beam gradually straightens towards C. The portion from B to C continues with the slope that we developed at B, and the slope and deflection remain continuous. The maximum deflection occurs at the free end C. Next, we can look at the bending moment. The bending moment is maximum at A, the fixed end, and it decreases towards B. At C, in the loaded region, it varies non-linearly due to the distributed load, and in the unloaded region, it is zero, since there is no load acting there. The bending moment is maximum at A and decreases towards point B. Since this is a cantilever from B to C with no load, there is zero moment in this region. Because the loading changes at B, we'll divide the beam into two regions and introduce separate section variables x1 and x2 for each segment. Importantly, by taking sections from the free end side, the choice of coordinate means that we don't need to calculate the support reactions at A. The internal bending moment can be written directly from equilibrium of the free end section, giving a much simpler moment expression, as we'll see, in each region. Let's first consider region 1, which runs from the free end C to point B. We define the coordinate x1 measured from C towards B, so in this region, x1 is between 0 and L minus A. The portion of this beam is unloaded, and there's no load at all acting between C and B. We take a section at a distance of x1 from C and draw the free body diagram of the right-hand segment. Since there are no external loads acting on this segment, equilibrium around the cut, so sum of moments around the cut equals 0, immediately leads to the moment x1 at that exposed n being 0. So in region 1, the bending moment is 0 throughout. This is exactly what we expected when we discussed the shape earlier. As we move to the end of the load, the bending moment reduces to 0, and in the entire overload overhang CB, it is identically 0. We'll now move on to region 2, which runs from B towards the fixed support A. We define a new coordinate, x2, measured from B towards A, so that x2 is between 0 and A. If we look at the top right-hand side, we can see a free body diagram from section CB, and then the internal forces and moments, and then the section from B to A starting. From region 1, we did establish that in the unloaded segment CB, the moment and the shear force equals 0. That means that no bending moment and no shear force are transferred across point B from region 1 into region 2. So at B, both the internal shear and bending moments are 0, and in region 2, the internal forces therefore develop entirely due to the distributed load acting between B and A. We'll now take a section at a distance x2 from B and draw the free body diagram of the portion between the cut and B. Over the length x2, the UDL can be replaced by its resultant Wx2 acting at its centroid located at x2 over 2. Applying moment equilibrium around the cut, so sum of moments around the cut equals 0, we get that minus the moment, due to our sign convention, minus Wx2 times x2 over 2 equals 0. And that simplifies to the moment equaling minus Wx2 squared over 2. So in region 2, the bending moment varies quadratically with x2, which is exactly what we expect under uniformly distributed load. The important conceptual point here is that region 2 does not inherit any shear or moment from region 1. Both are 0 at B, so the internal force system in this region is generated solely by the applied load. We can now summarize the bending moment expressions for the two regions. For region 1, from C to B, the moment is 0, and in this case x1 is between 0 and L minus A. This confirms that the entire overhang CB carries no bending moment and therefore has 0 curvature. For region 2, from B to A, the moment is minus Wx2 squared over 2, and x2 is between 0 and A. Here, the bending moment varies quadratically with distance into the loaded region as expected for uniformly distributed load. This piecewise definition reflects the physical behavior of the beam. And now, with the bending moment fully defined in both regions, we're ready to begin the integration process. We start by integrating the bending moment once to obtain the slope. We need to do this separately for each region. So for region 1, where we found that m equals 0, the slope expression becomes an integration of 0, and so we only have the constant of integration, C11. This tells us that the slope in region 1 is constant, which is consistent with the fact that the curvature is 0 in this region. For region 2, where x2 is between 0 and A, we have a moment of minus Wx2 squared over 2, and integrating once gives us Wx2 cubed minus Wx2 cubed over 6 plus the constant of integration C21. As you note here, and as in previous examples, the constants of integration are numbered so that the first index indicates the region, so 1 or 2, and the second constant indicates from what integration they came out of, so in this case, both from integration 1. At this stage, we have two constants of integration, one for each region, and we'll determine them later using boundary conditions and continuity conditions. Now we integrate once more to obtain the deflection expressions in each region. Again, we treat each region separately. So for region 1, when the previous integration gave us C11, integrating again gives us C11 times x1 plus C12. So in region 1, the deflection is linear, and that matches the physical idea that segment CB is straight. For region 2, where x2 is between 0 and A, the slope expression was minus Wx2 cubed over 6 plus C21, and integrating that once again gives us minus Wx2 to the power of 4 over 24 plus C21 times x2 plus C22. At this stage, we now have four unknown constants, C11, C12, C21, and C22, which we will determine using boundary conditions at the fixed end and continuity conditions at point B. So let's now look at these conditions. We'll start with the boundary conditions. Now, because we have used two different coordinates, we need to be very careful about where the fixed end is in terms of the regions. The fixed support is at point A, so A is in region 2. In region 2, coordinate x2 is measured from B towards A, so the fixed end corresponds to x2 equals A. At the fixed end, both the deflection and the slope are 0, and therefore the boundary conditions are y2 when x2 equals A equals 0, and y tag 2, or the slope in region 2, when x2 equals A equals 0. These two conditions allow us to determine two of the constants in region 2. Let's now look at the continuity conditions at point B where the two regions meet. Even though the loading changes at B, the beam itself is continuous, so it cannot have a sudden jump in deflection or a kink in its shape. And that means that both the deflection and the slope must be continuous at B. Because we use two coordinate systems, we express point B in each one. In region 1, x1 is measured from C towards B, so at point B, x1 equals L minus A. In region 2, x2 is measured from B towards A, so at B, x2 equals 0. So the continuity conditions are, for the slope from region 1 when x1 equals L minus A has to equal the slope from region 2 when x2 equals 0, and the deflection for region 1 when x1 equals L minus A has to equal the deflection for region 2 when x2 equals 0. Together with the two boundary conditions at the fixed end A, this gives us a total of 4 equations for the 4 unknown constants. We'll now start substituting the conditions to determine the constants. First, we apply the fixed end slope condition at A. In region 2, the slope expression was minus wx2 cubed over 6 plus c21. At the fixed support, x2 equals A, and the slope must be 0. So substituting A instead of x2, we get the expression that minus wa cubed over 6 plus c21 equals 0, and that gives us that c21 equals wa cubed over 6. We can substitute that back into the slope expression for region 2, and we get minus wx2 cubed over 6 plus wa cubed over 6. So the slope in region 2 is now fully defined. We can also substitute the value back into the deflection expression for region 2. So substituting c21 into the expression gives us minus wx2 to the power of 4 over 24 plus wa cubed over 6 times x2 plus c22. At this stage, only c22 remains unknown in region 2, and we'll determine it using the deflection boundary condition at A. So let's apply that fixed end boundary condition, 0 deflection at A. In region 2, we found the deflection expression and simplified it in the previous step, and at the fixed support, as we said, x2 equals A, and the deflection must be 0. So substituting x2 equals A gives us minus wa to the power of 4 over 24 plus wa cubed times A, so again a to the power of 4 over 6, plus c22. Combining the terms and simplifying gives us that c22 equals minus wa to the power of 4 over 8. And now the deflection expression for region 2 is completely defined. Region 2 is now fully determined, and we can move on to applying the continuity conditions at B to determine the remaining constants for region 1. Let's now apply the continuity of slope at point B. So at point B in region 1, x1 equals L minus A. The slope in region 1 was C11, so there's nothing to substitute here, that remains C11. We already defined the slope for region 2, that was minus wx2 cubed over 6 plus wa cubed over 6. Here we do need to substitute x2 equals 0, and so the first term falls, and we remain with only the second term, wa cubed over 6. And so equating these two expressions, the slope from region 1 at point B with the slope at region 2 at point B, gives us that C11 equals wa cubed over 6. At this point, the slope for region 1 can be fully assessed, and it is wa cubed over 6. This confirms that the entire unloaded segment CB has a constant slope, and it equals the slope developed at point B. We'll now apply the second continuity condition at point B, which is the continuity of deflection. First, we'll write the deflection expression in region 1, and we'll substitute C11, which we just found on the previous slide, giving us a deflection of wa cubed over 6 times x1 plus C12. Into that, we'll substitute x1 equals L minus A because we're at point B. Simplifying the equation, we get that wa cubed over 6 times L minus wa to the power of 4 over 6 plus C12. Next, we'll look at the expression for the deflection at region 2. We already fully developed this, so this is the final expression, and all we need to do in this case is substitute x2 equals 0. So doing that, the first two expressions that depend on x2 immediately fall off, and we remain with minus wa to the power of 4 over 8. We now need to equate the deflection from region 1 with the deflection from region 2, which we do at the very end of this slide. So starting off with the equation that we found previously, we need to isolate the term C12 and rearrange and organise the terms left over on the right-hand side. If we do that, we are left with wa to the power of 4 over 24 minus WA cubed times L over 6. This determines the last unknown constant. At this point, all four constants have been found and the elastic curve and the slope expressions are fully defined in both regions. So let's summarize and write out the complete expressions for both regions. Let's start with the deflection. So for region 1, where x1 runs between 0 and L minus a, we've got an expression of EI times the deflection in region 1 equals WA cubed over 6 times x1 plus WA to the power of 4 over 24 minus WA cubed times L over 6. We can note that all the units are similar. So in all of these terms, we have W, the distributed load, times a unit of length to the power of 4. In region 2, the expression for EI times Y2, deflection in region 2, is minus WX2 to the power of 4 over 24 plus WA cubed over 6 times x2 minus WA to the power of 4 over 8. And in this case, x2 runs between 0 and a. The corresponding slope equations give us that EI times the slope in region 1 equals a constant WA cubed over 6, where x1 runs between 0 and L minus a, and that confirms again that the unloaded segment CB has a constant slope, and the slope in region 2 times EI equals minus WX2 cubed over 6 plus WA cubed over 6, where x2 once again runs from 0 to a. At this stage, the cantilever response is fully defined, and we can evaluate slope and deflection at any required location. All we need to do is determine if that location is in region 1 or in region 2 and use the appropriate x1 or x2 and substitute that into the slope or the deflection equation. Now we were asked to determine the slope at point B, and since point B is the point joining the two regions, we can evaluate the slope using either expression, either substituting x1 equals L minus a into the slope for region 1 or x2 equals 0 into the slope for region 2. It's convenient to use region 2 and just substitute x2 equals 0, and the slope in region 2 was minus wx2 cubed over 6 plus wa cubed over 6. Substituting that x2 equals 0, the first term falls off and we're left with wa cubed over 6. This exactly matches the slope obtained from region 1, which confirms continuity. To get the actual slope, we just need to divide the expression by EI, and so theta b, the slope at B, is WA cubed over 6EI. And this is the constant slope that's carried through the entire unloaded segment from B to C. Additionally, we were also asked to determine the deflection at point B. So once again, since B is the point between the two regions, we can evaluate either using region 1 at point B or region 2 at point B. Let's take region 2 and substitute x2 equals 0. In this case, substituting x2 equals 0, you can see that the first two terms reduce to 0, and we're left with minus WA to the power of 4 over 8. Once again, dividing by EI, we can get the displacement at B, and the displacement at B, as we said, equals minus WA to the power of 4 over 8 EI. The minus sign indicates a downward displacement, which is consistent with the load. Thank you for joining me. I hope you found this useful, and I hope you join me again for some more structural engineering.